Welcome to the Science and Sleep program, where magical knowledge meets ultimate relaxation. Relax your body, take a deep breath, and let your mind drift slowly in the quiet space of the evening. Tonight, we will open the door of time and return to a completely different Earth, where fire and lava reign, where oceans have not yet formed and continents have not yet appeared. Let us explore this fiery planet together, where everything we know about life and nature has never existed. If you want to follow the full, exciting journey and not miss any mysteries of the primordial Earth, don't forget to hit the subscribe button and turn on notifications so we can experience it together until the end of the video. Now, imagine stepping into an Earth never seen before, where everything we are familiar with has yet to appear. No blue seas, no dense forests or mountains, only a gigantic fiery sphere, its surface boiling in a sea of glowing lava. Streams of molten rock flow, dark gray and fiery red, forming rivers of fire winding across the planet, radiating heat that makes the air tremble. Smoke and steam rise, mixing with sulfur and carbon dioxide to form a thick veil in the sky, allowing only the fiery red rays of the young, intense sun to penetrate down onto the molten surface. This is not the peaceful Earth we know, but a compact universe of chaos where every moment is in flux and each second is a fierce battle between gravity, heat, and matter. In this scene, what we call terrain is merely a network of lava continuously arranging, blending, and regenerating itself. There is no stable ground to walk on, no oceans to surf, only heat and pressure forming new layers of rock, melting again and solidifying once more. Tiny mineral particles constantly collide and merge, forming the foundations for mountain peaks, for the future crust, for the oceans that will appear billions of years later. Every chemical molecule, from iron to silicon, from oxygen to carbon, is finding its place in this feast of heat and pressure. Even the basic elements that make up you, me, and all living beings today are floating in the lava or evaporating into the air. But the primordial Earth is not only fire and rock. From violent collisions with other celestial bodies, enormous heat is released, raising the planet's temperature to nearly unimaginable levels. The outer surface constantly moves, bending under gravitational forces and impacts from meteorites. Each collision not only melts the surface further, but also disperses and redistributes elements, making the Earth richer in minerals, preparing for the formation of oceans, the atmosphere, and life. Every drop of lava, every wave of heat, every suffocating gas stream is a first step in the creation of the planet we now call home. At the center, the Earth's core begins forming from molten iron and nickel, flowing along slow convection currents. This hot core not only retains heat, but also generates a magnetic field, an invisible shield protecting the planet from dangerous radiation from distant space. The iron particles in the core were once part of ancient stars that exploded billions of years ago, now being recycled in the primordial Earth. This reminds us that every small part of today's planet is the result of great, distant, and violent events beyond ordinary imagination. Above the surface, the atmosphere is still unstable. Carbon dioxide, water vapor, methane, and ammonia mix with mineral particles rising from the lava, forming a hot, heavy, and dangerous haze. Light filtering through this layer of gas appears only as glowing red patches, shining onto the lava seas like strange beams. The dense air full of chemical compounds is the first foundation for the complex reactions that will lead to the formation of oceans and later life. These reactions occur silently, in the isolation of an unshaped planet, but lay the groundwork for everything that is about to happen. In the primordial sky, the moon has not yet appeared, but meteoroids and asteroids continuously collide with Earth. One of the massive impacts will eventually create the moon, an event shaping the orbit and living conditions on the planet. Each impact releases enormous energy, deforming the surface, melting rocks and minerals, and generating shockwaves spreading across the planet. In this chaos, the chemical foundations for oceans, atmosphere, and life begin forming, like invisible seeds incubating within the lava and hot smoke. Not only Earth, but the early universe also contributes to this journey. Before the sun was fully formed, the solar nebula drifted around what would later become the planetary system. Within the nebula, dust, ice, carbon, and heavier elements from dead stars collided, merged, and formed primitive planets. Each dust particle carries a history of billions of years, and each collision is a step toward Earth. This planet did not form randomly. It is the result of continuous mergers, collisions, compression, and restructuring, a violent dance of matter, gravity, and heat. Over millions of years, the Earth's crust begins to gradually cool, but not enough to form oceans. Lava still flows continuously, smoke and toxic gases still cover the sky, and sunlight remains obscured by the glowing red veil. Yet, within these harsh conditions, the foundation of life is forming. The first chemical compounds bond together, clinging to the surfaces of forming minerals, creating increasingly complex structures. The seeds of oceans, primitive organic molecules, and energy-rich minerals are all waiting for the moment to blossom into a watery, green, and vibrant planet billions of years later. And here is the miracle. Everything we see around us today, from vast oceans and lush forests to humans and all living beings, originates from this sea of lava. From scorching chaos, from colossal collisions and layers of toxic gases, Earth began weaving its story. The initial ferocity did not destroy. It laid the foundation for everything, a fiery planet, yet also the cradle of life, a place where in every speck of dust, every stream of lava, the echoes of the primordial era still linger. As Earth gradually grew and its outer crust still seethed in seas of lava, the planet began entering a new phase, cooling. The enormous heat from collisions and lava flows started to dissipate into space. A semi-solid crust formed, temporarily dividing magma regions from areas gradually solidifying. But temporarily is the key word here. Continuous collisions from asteroids and meteorites still occasionally punctured this crust, igniting new lava flows, continuing to melt the surface and replenishing heat in the core. Nevertheless, the cooling process allowed miracles to happen for the first time in the planet's history. Minerals began to stabilize, and gases from primitive chemical reactions started accumulating around the planet, forming a primordial atmosphere. This atmosphere was not like the air we breathe today. Instead of oxygen, it was filled with carbon dioxide, methane, ammonia, water vapor, and impurities from lava and volcanic gases. Strong winds blew through this layer, dispersing molecules across the planet, creating a heavy, glowing red sky, sometimes flickering in the light of the boiling lava below. This atmosphere, though suffocating and toxic, acted as a shield for the early planet against cosmic radiation and retained heat, allowing chemical processes to occur more steadily than if the surface had cooled abruptly. Alongside the formation of the atmosphere, water began to appear, but not in the vast oceans we know. Water vapor from the lava rose, and upon meeting cooled mineral particles, condensed into dense clouds. The first drops of water fell onto the semi-solid crust, meeting the scorching lava and instantly evaporating, but this process continuously accumulated important chemical compounds. These fleeting drops of water were the precursors of the first oceans, the seed droplets, nurturing future life. In the magma oceans, minerals and heavy metals such as iron, nickel, and copper separated according to weight. Lighter elements, silicon, magnesium, calcium, and volatile substances rose to the surface, creating a new crust. Chemical reactions occurred quietly in the magma, combining with primitive gases and water to form simple organic compounds, the first building blocks for more complex molecules. These reactions acted like a gigantic laboratory, where nature continuously experimented with ways to combine atoms to create life. During this time, Earth continued to collide with celestial bodies. Some major impacts, like the collision with the body Theia, ejected a massive amount of material into orbit, forming the Moon, the permanent companion of Earth. The Moon would later influence tides, climate, and the development of life. But for now, it had not yet formed, and violent impacts still shaped the planet in fundamental ways, melting rocks, dispersing elements, and reshaping the surface. The miracle is that, despite the apparent chaos, Earth was preparing for a special future. The gradually cooling magma formed stable minerals, organic compounds accumulated in the condensed water, and the dense atmosphere retained heat, all essential elements for the planet to become capable of supporting life. Every eruption, every collision, every moving magma flow contributed to preparing for life, like an invisible artist gradually sculpting the planet. Over millions of years, the temperature differences between the molten core and the cooling crust began generating strong convection currents in the magma. These currents not only distributed heat evenly, but also promoted the formation of tectonic plates. crustal slabs gradually separating and converging. This was the beginning of tectonic phenomena, which billions of years later would form mountains, valleys, and volcanic ranges. The ground was no longer a homogeneous layer of rock, but became dynamic, constantly transforming and forming complex structures. Furthermore, the first oceans began to form where cooled lava met condensed water, creating liquid. These primitive water regions were rich in minerals and simple organic compounds, becoming ideal reaction pools for complex molecules. Here, basic elements like carbon, hydrogen, nitrogen, and oxygen began combining into higher structures, the precursors of the first cells. From an external perspective, these water regions would appear as sparkling points on Earth's glowing red surface, signaling the places where life would first find a foothold. All of this, boiling magma, toxic gases, primitive water, minerals, continuous collisions, was not merely chaos. It was a sophisticated system where everything served the stable formation of the planet. Earth, from a molten sphere through gravity, heat, and chemistry, gradually transformed into a structured planet with a changing surface, an atmosphere, water, and eventually the ability to sustain life. What seemed destructive was in fact preparatory, and everything we see today, blue seas, forests, mountains, originated from this violent sea of fire. As the crust continued to cool and the first oceans stabilized, Earth became ready for a new chapter. The emergence of complex organic compounds, primitive cells, and chemical reactions that would lead to life. This was an era in which nature both destroyed and created, a time when the planet demonstrated its extraordinary capacity for renewal and adaptation. Every eruption, every rushing lava flow was the first step toward the world that you, I, and all living beings today call home. As the surface of Earth gradually cooled, the fiery magma slowly solidified, forming fragile yet crucial layers of crust. These were not merely temporary protective coverings, but the first foundations of the terrain that oceans, mountains, and valleys would later occupy. These crust layers continuously formed, fractured, and were recycled, as if the planet were rehearsing for long-term stability. This gradual cooling process did not occur uniformly. Each collision from remaining small celestial bodies, each new magma flow from the hot core, and each primitive volcanic eruption returned Earth to a state of intensity. Yet it was precisely the oscillation between molten and cooled states that allowed matter to stratify, heavy elements to sink into the core, light elements to rise to the crust, and diverse minerals to distribute in ways still observable today in ancient rocks. At the same time, water began to accumulate on the planet's surface. Initially, it existed only as dense vapor rising from hot magma, then condensed into the first droplets falling onto the temporarily cooled crust. These droplets, though meeting extremely high temperatures and evaporating instantly, triggered a series of important chemical reactions. Minerals from the magma mixed with water vapor, carbon dioxide, and other compounds, forming weak acids, salts, and other inorganic compounds. These were the building materials for prebiotic chemistry, the first steps toward life. The primordial oceans, when finally present as stable liquid water, provided an environment for these reactions to occur continuously, a gigantic natural laboratory requiring no human intervention. The atmosphere also gradually became more stable. Carbon dioxide, nitrogen, ammonia, sulfur dioxide, and water vapor accumulated, forming a dense gaseous layer around the planet. Sunlight passing through this layer was scattered and reflected, creating a mystical red-orange halo globally. The air was oppressive and hot, but this gaseous layer retained heat, helping Earth maintain the thermal energy necessary for chemical reactions and to keep liquid water on the surface. It also protected the young Earth from intense solar radiation, acting like an invisible armor shielding the planet from dangers in space. While the crust cooled and the atmosphere stabilized, the Moon, the companion born from the massive collision with Theia, began shaping Earth's rotation. The Moon's gravitational pull stabilized the planet's axis, preventing Earth from tilting continuously under the influence of the Sun and other planets. This stability, though subtle, was crucial for a relatively stable climate, allowing the primordial oceans to persist and enabling chemical processes to develop in increasingly complex ways. Additionally, the early tides generated by the Moon stirred the oceans, circulating water, minerals, and energy, providing favorable conditions for prebiotic chemical reactions to occur continuously, like a natural engine driving biological complexity from the very beginning. The cooling process affected not only the surface, but also deep interior processes. The molten core began generating a primitive magnetic field through conductive convection currents. This nascent field, though weak, became a protective shield for Earth against solar radiation, a vital factor for future life forms. The combination of gradually solidifying magma, the formation of the first water, accumulating atmosphere, and the primitive magnetic field constituted the first steps toward creating an Earth capable of sustaining life, a planet transforming from molten chaos into a world with latent order. From a broader perspective, the scene was a masterpiece of chaos. Magma oceans still existed over vast areas, thin dark crust layers floated up and sank, and small impacts continued, occasionally igniting new magma flows. Earth was not yet stable, but this state fueled creativity. Each cooling magma flow, each forming and dissolving crust layer, facilitated the even distribution of minerals and useful elements, preparing for future chemical reactions and more complex structures. Viewed from orbit, Earth would appear as a radiant, constantly vibrating sphere, a testament to the concurrent forces of destruction and creation in the universe. As the surface and atmosphere became increasingly stable, the primordial oceans began to truly take shape. Pools of liquid water concentrated in low areas where magma had cooled and the crust had hardened sufficiently. These oceans were not yet the vast seas we see today, but they were large enough to contain primitive elements and organic compounds, creating favorable conditions for ongoing chemical reactions. Here, carbon, nitrogen, hydrogen, and other elements had the opportunity to combine, forming increasingly complex compounds, preparing for life to emerge over the following hundreds of millions of years. Everything occurred in a delicate balance: the ferocity of magma, collisions, toxic atmosphere, primitive water, and the stabilizing moon, all combined to create conditions upon which any future life forms would rely. The young Earth, from a chaotic ball of fire, took its first steps toward stability, turning the remnants of catastrophe into a foundation for a planet capable of sustaining life. And from the cooled rocks, the first droplets of water, and the early chemical reactions, the billion-year-long story of life quietly began to be written. As the fragile crust layers rose and vanished on the surface, the planet began performing a persistent kind of dance: differentiation. Under the pressure of heat and gravity, lighter materials such as silicon, aluminum, and aluminum-rich minerals began to float, forming temporary crustal plates amid the vast magma oceans. Conversely, heavier materials like iron and nickel sank deep, creating the foundation for Earth's core. This stratification, a natural yet violent process, laid the groundwork for future continents. Each crustal plate rose and then sank, but the lighter minerals continuously accumulated, gradually forming stable points within the ever-moving magma sea. This was the stage in which Earth practiced for long-term stability, transitioning from molten chaos into early order. Differentiation was not merely a physical phenomenon, it was also a gigantic chemical laboratory. The rising crustal plates, though brittle and fragile, still interacted with the dense atmosphere. Water vapor, carbon dioxide, and sulfur dioxide reacted with hot rock, triggering primitive chemical reactions that formed new minerals and prebiotic compounds. The first raindrops, condensing from vapor and falling onto these rocks, began circulating nutrients across the planet. Each rainfall, each lava flow, was an initial step toward life, even though no living being existed to witness it at that time. While the surface and crustal plates continuously transformed, the magma below remained seething, maintaining temperatures high enough for new rock layers to form and break apart, as if Earth were training for endurance. These flows not only created temporary terrain, but also controlled the distribution of minerals. Light silica plates merged, accumulating into primitive islands, land masses able to endure longer than the smaller floating fragments around them. It was these floating fragments that later allowed the first continents to begin forming, laying the foundation for the landscape we now call Earth. The continuous impacts of asteroids and comets not only shattered crustal plates, but also supplied additional elements and heat, driving change. Each collision was both destructive and creative, It ignited magma, broke old crusts, and introduced new elements into the evolving chemical mixture. This demonstrates that even amid extreme chaos, Earth advanced toward stability, gradually creating an environment capable of supporting life. Above, the atmosphere remained dense and violent. Dust, sulfur dioxide, and carbon dioxide created hazy layers, scattering sunlight into mystical shades of red, orange, and purple. Every lightning strike, every volcanic plume was a source of immense energy and charge, stimulating chemical reactions in the atmosphere. From these reactions, simple organic compounds began forming, laying the foundation for more complex molecules over millions of years. The space between the magma below and the gaseous layer above was where planetary chemistry unfolded, although any living being present would have been unable to survive these harsh conditions. The magma oceans, brittle crust, and dense atmosphere formed a synchronized system. Heat from below, gases from above, water accumulating in low areas, and light minerals collecting on the surface. This was the period in which Earth learned to balance between molten and cooled states, between destruction and creation. Floating crust fragments acted as temporary islands, retaining precious minerals, while the magma below continued to circulate and enrich the crust. Gradually, certain regions began to stabilize. Heat from the underlying magma remained strong, but the crust in these areas was thick and dense enough to persist longer than other regions. These stable points became the seeds of the first continents. They became places where primordial oceans could gather, where rain from the dense atmosphere flowed and began forming small lakes, the precursors to rivers and seas of the future. These were the first fragments of order in the molten world, where life could find the chemical foundation it needed over millions of years. Each gas layer, each crustal plate, each magma flow contributed to transforming Earth from a chaotic ball of fire into a planet capable of stability. Every collision, every erupting lava flow, every first rainfall was a small step toward order. The fragmented and brittle crust layers were continuously recycled, ensuring that elements and minerals were evenly distributed, providing the raw materials for complex chemistry and billions of years later, for life. Viewed from above, this scene was both fierce and marvelous. The primordial Earth was a continuous dance between destruction and creation, where magma, rock, water, and atmosphere interacted constantly, laying the foundation for the future. This was an era in which every step was fiery, every change intense, but it was through these steps that the planet could progress toward a day of order, stable oceans, and life. Amid this fierce landscape, the planet quietly took its first steps toward order. As lava flowed, the young crust rose and then sank. Lighter mineral fragments rich in silicon and aluminum began to accumulate, finding balance within the sea of fire. They could not form stable continents immediately. The temperature was too high, collisions were constant, and the dense volcanic atmosphere still prevented any stability. Yet it was in this chaos that Earth was learning to recycle and accumulate, preparing for future geological leaps. Each lava flow, each eruption, transported minerals and energy to the surface, mixing all components, creating the groundwork for future landmasses. The sky remained a vivid and harsh panorama. Dust, sulfur dioxide, methane, and carbon dioxide mingled into a dense fog, scattering sunlight into strange shades of red, orange, and purple. Each lightning strike cut through the gaseous veil, illuminating flowing lava, highlighting the slow molten streams and brittle crust plates twisting and fracturing. These gaseous clouds were not only fiercely beautiful, but also a gigantic natural chemical laboratory where primitive organic compounds formed, laying the foundation for life millions of years later. From an observer's perspective, the red sky stretched like an eternal sunset, reflecting volcanic smoke plumes and molten lava flows. The lava flows on primordial Earth were not merely a surface phenomenon, but a language of deep mantle convection. Heat from below pushed magma upward, cooler plates sank, and the surface mirrored the chaos beneath. Faster flowing molten streams twisted like fiery threads, creating channels, ridges, and grooves, while denser, cooler flows bent into jagged, uneven crust sheets, like shattered glass. Each movement, each collision formed complex geological structures, precursors to valleys, plains, and plateaus that would come later. As lava flowed, water from the atmosphere condensed, creating the first rains scattered over the molten surface. Water could not persist long, instantly evaporating or boiling upon contact with magma, but each tiny drop carried minerals blending into cracks and depressions. Chemical reactions occurred. Carbon dioxide and methane interacted with hot rock. Sulfur dioxide dissolved in temporary water pools, forming prebiotic compounds. Each water droplet, fleeting as it was, marked an initial step in the planet's chemical cycle, preparing for the stable oceans of the future. The floating crustal fragments in the magma ocean, though brittle and short lived, acted as temporary islands where light minerals accumulated. As magma cooled, new basalt layers formed, the surface partially solidified but remained continuously disrupted by underlying magma flows. This recycling process, repeated over millions of years, created the first foundations for continents. There was no permanence, no endurance. Yet this instability was an essential preparation, allowing Earth to mix minerals and energy thoroughly, creating a surface rich in potential for life to develop later. Each volcanic eruption was a powerful event, reshaping terrain and atmosphere. Lava jets soared into the sky, spreading volcanic material across the surface, and as it settled, it merged with existing flows, altering the direction of magma. This was a world with no absolute stability. Yet, through continuous recycling, minerals and energy were evenly distributed, and the surface gradually reached a relative equilibrium. Lava flows acted like veins, carrying energy from Earth's fiery heart to the surface, simultaneously destroying and building. From above, the planet resembled a living organism, vibrating with bright magma veins on the surface. Colors shifted continuously. Brighter areas marked hot flows, darker patches indicated cooler, denser regions. The lava streams branched, merged, and diverged, forming a vast network like rivers today, but far hotter and more violent. They were invisible sculptors, carving channels, ridges, plains, and plateaus, creating the geological foundation for future continents and oceans. The interaction of lava, volcanic gases, and primitive water created an environment full of energy and chemicals. The dense atmosphere retained heat, sustaining feedback loops between magma and volcanic gases, ensuring the surface remained molten. Yet at the same time, the lava flows themselves acted as the planet's first cooling system. As they cooled, they released heat into space. Volcanic rock layers accumulated gradually, forming a foundation for solid ground. Each flow, whether brief or prolonged, contributed to shaping Earth from a chaotic ball of fire into a planet capable of sustaining land, oceans, and life. Overall, primordial Earth was both fierce and mesmerizing, a world of fire, volcanic gases, and flowing lava where everything changed continuously. Yet it was within this chaos that the planet laid the first bricks for complex geology for the continents and oceans of the future. These rivers of fire carried not only magma, but also potential, energy, and essential elements, everything Earth needed to transform from a chaotic world into a habitable planet. Amid the storms of magma and the thunderous sounds of cosmic collisions, Earth began to listen to a different rhythm, the rhythm of water. Ice droplets from comets, water crystals remaining in celestial objects, for the first time came into contact with the molten surface. They did not fall onto a stable surface, but into a seething ocean of lava. The water vapor rose immediately, twisting through dense gas currents, creating heavy mist that filled depressions and cracks. From above, they appeared as silver streams winding through a sea of blazing red fire, quickly vanishing but leaving behind chemically crucial traces. Each impact that delivered water also brought tremendous energy, tossing the magma surface, igniting new explosions, mixing water with molten rock and volcanic gases. This was the beginning of a previously unseen natural cycle. Water cooled the crust, magma provided heat, and chemical reactions produced prebiotic compounds. Tiny particles of ash, rock, and minerals rose, collided with water vapor and sulfur dioxide, dissolved, and precipitated in temporary water pools. In this moment, the essential elements for life, carbon, nitrogen, phosphorus, began to find their first foothold on the planet. Gradually, the small water pools expanded, becoming molten magma lakes where magma and water met, boiled, and evaporated into dense clouds. The water did not merely rise, it carried chemical compounds from the magma into the atmosphere. Primitive cycles formed like the first rivers, but they did not flow solely by gravity. They flowed by energy, pressure, and temperature. Water was retained in deep pits and crustal cracks, And thanks to magma circulation, these water channels gradually stabilized, although they were always disrupted by eruptions and impacts. Meanwhile, the atmosphere was evolving in its own way. Carbon dioxide, methane, and sulfur dioxide mixed with water vapor, forming a dense mist that retained heat and kept the crust relatively molten. Lightning strikes pierced this layer, triggering chemical reactions and producing primitive organic compounds. Earth was no longer just a ball of fire. It was a colossal laboratory where matter combined, broke down, and recombined continuously. Each eruption, each impact crater, each water droplet was part of the planet's first chemical lessons. Lava flows continued, creating new magma plains, with temporary solid crust fragments floating on the lava sea. When water met these fragments, rock layers cooled rapidly, forming primitive platforms, the first protocontinents. There was no absolute stability, but the combination of magma, water, and volcanic gases laid the first bricks for a solid surface. This was the precursor to real oceans, to the differentiation between land and sea, and ultimately to habitable environments. Cosmic impacts continued unabated, but their nature had changed. Part of their energy was absorbed by magma pools and primordial oceans. Water evaporated and formed clouds, reducing total destruction. At the same time, water from comets gradually accumulated, forming larger lakes, creating the first safe zones on the surface, though still insufficient to sustain life. These water pools became heat reservoirs, mixing with minerals and organic compounds, like natural cauldrons where chemical reactions could occur continuously. From above, Earth's surface looked like a dynamic map. Glowing red lava flows winding among temporary silvery water pools, columns of sulfur and carbon dioxide rising high, flashes of lightning piercing the dense atmosphere. The sound continued relentlessly, but higher notes emerged, the hiss and sizzle of water meeting magma, the small pops of gas bubbles bursting. This was a polychromatic symphony where fire, water, and impacts created a rhythm, gradually blending into a song of creation. The presence of water also changed how lava flowed. Lava encountering water cooled faster, forming temporary solid crust layers, guiding the direction of subsequent magma flows. Old lava streams were fragmented, forming channels and branched magma plains. Small water cracks and pools gradually became primitive geological boundaries, sites of mineral and energy accumulation. Earth slowly learned to balance internal heat with external cooling, a survival rhythm that would sustain the planet for millions of years to come. Remarkably, in this chaos, lighter minerals rich in silicon and aluminum began to stabilize in temporary water zones. Floating molten crust fragments, held in place by water and magma, formed the foundation of the first protocontinents. Each layer of cooled magma, each rising lava flow, each evaporating water column contributed to a primordial geological structure, a precursor for the later formation of continents, oceans, and habitable environments. From a modern perspective, traces of this process can be seen in basalt rocks, surviving minerals, and Earth's ancient crust. Each eruption today, each lava flow, each dust storm is a recollection of primordial Earth. Magma lakes, rivers of fire, and cosmic impacts are lessons in energy, recycling, and the planet's ability to self-balance, demonstrating that chaos can create order, and from the fiercest storms of fire, life would one day take root. As the storm of celestial bodies gradually subsided, Earth was still not at peace. Although the number of asteroids decreased, the marks of impacts remained etched on the glowing red magma surface. Deep craters, enormous volcanic mouths, and newly formed basalt plains were still scorching under a crust striving to solidify. The chaotic atmosphere, blending carbon dioxide, sulfur dioxide, and water vapor, kept the sky ablaze with eruptions, lightning, and reflected flashes from impact craters. This was a time when every moment could become a geological event, a burst of erupting lava, a temporary water pool boiling, or a small collision from a remaining space rock. Together, they created a fierce symphony with an unpredictable rhythm. In the deepest depressions, water from comets began to accumulate, no longer completely evaporated by the heat of magma. These primordial water pools resembled enormous heat pockets where magma and water interacted in complex chemical reactions. Steam rose, mingling with volcanic gases, forming dense mist columns that dimmed the light from recent impacts. In brief moments of stillness, the only sounds were the hissing of boiling water and the popping of gas bubbles bursting in the magma. These were the primordial melodies of life, not yet formed but existing at the necessary energy and chemical levels. Cosmic impacts were no longer as frequent as before, but each occurrence still produced powerful effects. A small asteroid striking Earth could vaporize magma regions, hurl molten rock into the sky, and create shock waves reverberating through primordial water pools. Each such collision was not only destructive, but also a chemical opportunity. Carbon, nitrogen, hydrogen, and organic molecules from the asteroid dispersed across the planet, mixing with water, rock, and the atmosphere. These molecules would become the precursors for later biological compounds. Strangely, it was these tremendous explosions, walls of fire, and violent shock waves that became the first building blocks for life. For Earth's surface, the crucial factor was not only the presence of water, but also that magma cooled long enough to form temporary solid crust. These crustal fragments floated on the magma sea, guiding subsequent lava flows and creating new channels. Lava was more than molten material. It was the first platform where heavier minerals sank, lighter ones floated, and essential compounds formed for the future. Water collected among these crustal fragments was not just temporary pools. They were primordial cauldrons where chemical reactions occurred continuously, accumulating energy, minerals, and organic molecules. From a modern perspective, what Earth experienced at this time can be reflected in Venus and Io. Venus, with its dense carbon dioxide atmosphere and sulfuric acid clouds, is a cautionary mirror, a planet similar to Earth, yet never escaping its massive greenhouse. Lava on Venus is not confined to volcanic rifts, but spreads across plains, engulfing all surfaces and creating a perpetually oppressive landscape. Looking at Venus, we see both ruthlessness and persistence. A planet still molten, still shaped by magma, but without water to temper the fury. This is an extreme image, a glimpse of Earth if it had failed to cool and balance its climate. Io, Jupiter's moon, offers a different picture. Continuous volcanism, unceasing lava flows, a surface needed by Jupiter's immense gravity. Io has no oceans, no soft atmosphere, and no tectonic plates to regenerate its crust. Its surface is in constant flux. Cooled rock fragments create black lava streams winding through the moon's bizarrely colored sulfur fields. Observing Io, one sees an amplified, frozen-in-time version of early Earth, revealing the ongoing processes of magma, volcanic gases, and heat energy that our Earth once experienced. Observing Venus and Io is not merely for viewing, it is learning. From them, scientists understand how lava flows, how volcanic gases affect the atmosphere, and how heat escapes continuously from a planet's core. They reveal early Earth in real time, a world where every element was interconnected: magma, water, gases, cosmic impacts, and light from explosions. This is a vivid model of planetary formation and self-regulation. In early Earth, each eruption, each impact crater, each column of lava was part of the process of creating a habitable planet. Water, organic molecules, and minerals did not appear randomly. They were produced and distributed by the very violence and intensity of the environment. The sound of magma, the explosions of impacts, the hissing of water and gas formed a grand symphony, constantly reminding that life emerges from chaos, from the conflict among material and energy forces. Looking to the future, Earth was not only a planet that had escaped its fiery age, but also the result of lessons written in lava and light. Venus and Io still exist, like siblings who never left their fiery youth, reminding us that formation and balance are long and continuous cycles. And in the light and shadow of the universe, Earth emerged from fire and water, from collisions and lightning, becoming the only place in the solar system where life could form, endure, and become aware of its own fiery past. When the first raindrops fell onto the glowing black volcanic crust, they did not merely evaporate. Each contact between water and hot rock was a chemical reaction. The still burning crust, not yet fully cooled, merged with the steam, forming gas streams containing dissolved minerals and metal ions from the basalt. These minerals began to form new compounds, the chemical seeds that would one day become part of the soil, oceans, and even living cells. The violent collision between these two elements, fire and water, generated a chemical energy that nothing else could replace. This was a moment when Earth was simultaneously destructive and creative, the simultaneous beginning of geology and biology. Beneath the surface, lava continued to twist and turn, seeking new paths to escape. When lava met water accumulating in impact craters or primordial lakes, a battle between hot and cold ensued. Lava not only cooled but also produced complex silicate minerals. The immense heat radiating from the molten rock caused water to evaporate continuously, forming towering steam columns that shrouded the planet's surface in smoke and vapor. This interaction was uneven. Near impact craters, water evaporated almost instantly, while in more distant areas, water could persist longer, allowing deeper chemical reactions to occur and generating richer compounds. Meanwhile, Earth's crust was constantly shifting. Some solidified rock fragments merged to form large plates, while others sank beneath the molten mantle, creating deep trenches from which new lava continued to erupt. These early movements were precursors to plate tectonics, but at this time, they were still chaotic without a clearly defined system. The Earth's surface was then a living map, continuously transforming, where magma, rock, and water competed for position on a vast natural stage. The light from volcanic eruptions and impact craters created strange halos in the sky, reflecting off the dense mist. Each light was a rhythm in the cosmic symphony of early Earth. The clouds of evaporated water mixing with carbon dioxide and sulfur dioxide in the atmosphere formed massive smoke columns, the sails of the atmosphere. The air became thick, hot, and oppressive, yet it was also where essential chemical reactions occurred, producing foundational compounds for future life. Early Earth was shaped not only from the outside, from cosmic impacts and cometary rain, but also from within. The planet's hot core continued to radiate heat, engulfing newly formed crust in powerful eruptions. Lava spewed from newly formed volcanic vents created vast basalt plains, pristine black lands where water could exist, albeit briefly. Over millions of years, the cycle of lava erupting, cooling, and solidifying gradually created a more stable surface, capable of retaining water longer, forming primordial lakes, and preparing for the first oceans. The combination of magma, water, and gases produced new minerals such as olivine, pyroxene, and feldspar, each with distinct chemical properties, uh, serving as the raw materials for future soil and rock. Carbon and nitrogen, previously trapped in the atmosphere or delivered by asteroids, combined with water to form weak acids, participating in the process of mineral weathering. This was the foundation for the first geochemical biological cycles, where chemical elements began to redistribute, enriching soil and water and preparing for life. The first raindrops, although evaporating immediately upon contact with hot rock, also left traces. They created cracks and channels on the surface, places that could later become rivers and streams. These flows, though temporary and brief, marked the beginning of water-driven terrain formation, a crucial factor for future ecosystems. Each instance of rain and evaporation was a record of geological history, an indelible scar on the planet's surface. In the sky, columns of steam, smoke, and sulfur dioxide reflected light from the lava, creating halos of orange, red, and yellow. The scene resembled a surreal painting, where Earth was both a furnace and a protective wall for the elements forming life. Rain and lava, steam and fire all merged into a chaotic symphony rich in creative potential. As the surface gradually cooled, rainfall increased, forming actual streams over the rock. The scorching water wound through old lava channels, blending with minerals and gases, producing more complex compounds. The crust was no longer merely a shield, but became a chemical stage where elements from magma, water, and the atmosphere interacted, setting conditions for life to exist in the future. And then, in this moment, Earth was no longer just fire. It became a world of rock and water, where traces of its fiery youth still remained, yet simultaneously made way for early balance. The black volcanic crust, the first primordial lakes, the smoke columns, and the rain all contributed to laying the groundwork for life. Each rock fragment, each raindrop, each vapor molecule was a chapter in the story of transformation, from primal fire to a planet capable of sustaining life. Over millions of years, this rhythm gradually stabilized. Fire no longer dominated everything, water began to accumulate, and the surface became durable enough for chemical elements to genuinely build up. This was when Earth began entering a period in which biochemical processes could arise. From the scorching surface to the primordial oceans, from magma to rain, from the oppressive atmosphere to the cracks for water flow, the entire planet had been prepared for life. yet still retained the blazing marks of its fiery youth. As the first depressions began to accumulate water, young Earth suddenly came alive to an entirely new rhythm. Steam from the intense rains continued to rise, but it no longer vanished immediately. The crust had thickened enough to retain heat within, allowing some water to persist longer on the surface. Small primordial lakes, initially boiling violently upon contact with hot rock, began to stabilize in sheltered cracks. They became early cradles, experimental pools that the planet created to test complex chemical reactions. Water met minerals, reacted with carbon dioxide, sulfur dioxide, and metallic compounds, producing new compounds that would one day form soil, oceans, and an atmosphere capable of supporting life. In every evaporating drop, a grand chemical program was unfolding, laying the groundwork for a geochemical balance that the young planet had never known. Prolonged rains generated the first streams on Earth's surface. Water flowed through cracks and impact craters, eroding and dissolving hot basalt, transporting minerals into lower depressions. These were the first foundations for the formation of rivers, a global network transporting water and minerals. Lava still flowed from volcanic vents, meeting water and evaporating into dense steam, but the more stable flows gradually paved the way for primordial lakes to connect, merging into larger basins. Each rainstorm was not merely a physical phenomenon, but also a chemical process, step by step establishing mineral cycles, guiding the planet from a molten chaos to a state capable of retaining water over long periods. Small primordial lakes combined into early seas. Water was no longer immediately driven away by excessive heat, but began forming stable regions where steam could condense continuously. The atmosphere, once suffocating with carbon dioxide and sulfur dioxide, gradually eased. Steam spread into higher atmospheric layers, forming massive, dense, and heavy cloud columns. Lightning still cut across the sky, illuminating the majestic scene of volcanoes, lava, and rain. But now it was no longer just a chaotic symphony, but a rhythm beginning to stabilize, reflecting the new balance emerging. Beneath the surface, magma still moved, submerging unstable crustal plates and creating new basalt plains. But the impact of fire was partially mitigated by water. Lava streams, when meeting water, erupted violently as steam, but simultaneously cooled, solidified, and formed thicker basalt, making the crust more resilient. As a result, water accumulated in depressions became stable, allowing the formation of lakes and primordial seas, laying the groundwork for future oceans. Each eruption now was not only destructive, but also an opportunity to create new structures on the planet's surface. The primordial oceans contained an extremely complex chemical composition. Water mixed with carbon dioxide, sulfur dioxide, methane, ammonia, and metallic ions from the molten crust. This mixture was highly acidic and rich in minerals, creating a diverse chemical reaction environment. In each drop of water and each column of steam, primitive biochemical reactions could begin, opening the first steps toward life. Outwardly, Earth remained chaotic, but within the primordial oceans, a hidden order was gradually forming. The continuous movement of water, fire, and atmosphere created massive cycles. Water from rain and celestial ice flowed downward, gathered in basins, evaporated, and then condensed again, repeating countless times. Minerals from the molten crust dissolved and redistributed, creating a rich and diverse geological foundation. Through these cycles, the oceans were not just a static body of water, but an active energy and chemical system preparing for complex biological reactions in the future. Primitive coastlines formed from the combination of solidified lava and water-filled depressions. Jagged, uneven shorelines reflected sunlight through the misty clouds, creating a surreal spectacle. Waves were not yet regular, but had their own rhythm, surging into cracks and deep depressions. These were the first areas where water and rock interacted over long periods, producing dissolved minerals and new compounds, thus laying the foundation for future soil and biosphere. Meanwhile, the early climate began to stabilize. Rain no longer disappeared immediately. Steam began to condense into prolonged storms. Primitive winds, arising from temperature differences between fire and water, transported steam and minerals, regulated planetary temperature, and dispersed essential compounds everywhere. This cycle was a grand planetary laboratory where natural elements tested, experimented, and optimized conditions for life to exist. Millions of years passed, primordial lakes merged, basins accumulating water grew larger, and eventually the first oceans formed. Earth's surface transformed from a blazing realm into a world of water, where sunlight reflected on the new oceans, the sky gradually cleared, and the planet's rhythm began shifting from chaos to relative order. The primordial oceans were not only a physical symbol of water, but also an embodiment of a new balance. Water and fire, steam and lava, gases and rock all began to cooperate, laying the foundation for the green Earth we know today. As the first islands rose above the water, young Earth suddenly became more diverse than ever. No longer just a blazing pan of fire and boiling water, the planet began to display its own distinctive features. Dark land masses undulating amid blue seas, where waves lapped against rocks, creating the first rhythms of the tides, and steam rising from the sea meeting hot rock, blending with mineral-rich air, carrying the pungent scent of sulfur and minerals, the characteristic aroma of a forming Earth. These islands were initially merely blocks of gradually cooling basaltic lava, yet they played a crucial role. They became foundations for rainwater to accumulate, flow into streams, form the first channels, transport minerals into the sea, and establish the early chemical rules for the nascent oceans. Each volcanic eruption, each flowing lava stream, was a new chapter in the story of land formation. Lava meeting water not only evaporated into steam, but also cooled and solidified into sturdy basalt layers, forming the initial geological foundations. Layer upon layer of accumulating lava raised the island above the water, creating a surface wide enough to withstand the impacts of waves, wind, and rain. The first islands, though small and fragile, symbolized the first stability in a world that was inherently chaotic. Waves washing against rock shores carried away weak fragments, but through this erosion, the first sediments were delivered to the sea, enriching the chemical and mineral composition of the ocean. The formation of land was not merely a matter of physical accumulation. Internal differentiation within the planet played a critical role. Lighter silicate rocks from the molten crust rose above denser basalt, creating land masses sufficiently buoyant to persist on the surface. These land masses were the proto-continents, the foundations of future continents. They were not yet complex continental fragments with sandstone, granite, or sediment, but they created essential unevenness on Earth's surface, where there was land, where there wasn't, thereby influencing the direction of ocean currents, forming the first weather patterns and regulating regional temperatures. The early protocontinents also began to affect the water cycle. When rain fell on the islands, water accumulated, forming streams and nascent rivers. The flow carried minerals from the rock into the sea while creating the first sediment layers on the ocean floor. This system both regulated water quantities and contributed to the chemical foundation of the atmosphere. Carbon dioxide from the atmosphere was partially absorbed into the water, interacting with minerals, reducing acidity, and allowing for the formation of stable compounds, the precursors to future life. The interaction between land and the primordial oceans also generated new dynamics in the water cycle. Ocean waves, guided by the islands, formed early currents, transporting heat, minerals, and steam across the planet's surface. Each rising island was a natural navigation station, altering wind directions, creating regions of rain and dryness, and generating climate diversity. These factors, though primitive, played an important role in regulating the planet and creating a more complex environment. While land began to form, volcanic eruptions continued relentlessly, reshaping the landscape. An island could be split, submerged, or connected to another by new lava flows. This was a harsh but necessary rule for Earth to learn how to balance destruction and regeneration. Each time, basalt cooled, became stronger, and the planet's surface gradually consolidated. Over millions of years, small islands accumulated into larger landmasses, sufficiently robust to influence climate and ocean currents, the first steps toward true continents. The emergence of protocontinents also began to reshape the oceans. Water had to follow new outlines. Waves striking rock shores generated flow dynamics, forming the first bays, channels, and straits. Sediments from the land settled on the ocean floor, creating a primitive geological foundation, enriching seawater with minerals, and establishing the first chemical rules. Water and rock began interacting continuously, leading to a more stable cycle where physical and chemical elements work together to regulate the planet. From space, the picture of young Earth could now be imagined. Vast blue seas, black streaks of volcanic islands undulating, steam rising from fissures, and rain falling steadily, creating the planet's new rhythm. Each island, each water basin was a step toward complexity, from primordial fire and water to land and ocean, where life could eventually emerge. The first islands and protocontinents, though rudimentary, laid the groundwork for geological and climatic processes, transforming Earth from a planet of pure fire into a world balanced between land, water, and atmosphere, a crucial precondition for life. In this context, Earth was no longer a monotonous world. Water, land, and volcanoes formed a symbiotic relationship, simultaneously destructive and creative, gradually bringing the planet toward greater stability. The image of lone islands amid blue seas was not only a physical landscape, but also a symbol of geological evolution, protocontinents, and the first rhythm of the water cycle, all of which would contribute to shaping the green planet we know today. When viewed from space, young Earth's initial chaos had now transformed into a complex yet more balanced rhythm. Volcanoes, the planet's fiery lungs, continued to breathe, releasing heat and gases into the atmosphere. Each eruption was a dialogue between the surface and the interior, between land and sky, between water and fire. Steam rising from molten lava not only generated rain, but also mixed with volcanic gases, creating the first storms, swirling clouds, and dense rain columns, enabling a continuous cycle between land, water, and atmosphere. For the first time, Earth developed a form of primordial climate cycle, where winds, rain, water vapor, and lava flows interacted to shape the planet's surface. Land, though still small and fragile, played a central role in this process. As basaltic islands emerged, they became anchors for rainwater flow and lava streams, forming primitive basins. Water accumulated on solid surfaces that forming the first streams that transported minerals from volcanic rock into the sea. These minerals dissolved, enriching the primordial oceans while interacting with a CO2 and sulfur-rich atmosphere, initiating the first chemical reactions leading to temperature stabilization and chemical balance. Harsh as it was, this process laid the foundation for future life. Lava flows into the sea not only cooled the crust but also formed new rock, expanding land areas and raising islands above sea level. Waves lapping against rocky shores created primitive sediment layers, settling on the seabed and gradually accumulating into the first geological strata. It was a strange but necessary combination. Fire shaped the land, water sculpted and eroded it, waves dispersed material, and volcanic gases formed the atmosphere. Thus, Earth gradually established a primordial biogeological cycle where all components interacted within a tightly linked system. The sky was always filled with ash and vapor, enormous smoke columns from volcanic eruptions forming dense clouds that reflected sunlight and moderated surface temperatures. This natural shielding protected the oceans and primitive land masses from extreme temperature fluctuations. From a distance, Earth appeared as a living entity. Blue waters, black volcanic rock, white clouds, and the red glow of molten peaks. Everything moved to its own rhythm, the rhythm of a planet learning to regulate its energy, learning to breathe more evenly. Steam columns rising from lava, mixing with CO2, nitrogen, and sulfur, created a rich chemical gas mixture, laying the groundwork for the modern atmosphere. Nitrogen stabilized and became a major component, while oxygen gradually appeared through chemical reactions in the oceans. Water, through continuous cycles of rain and evaporation, regulated water quantities, stored heat, moderated climate, and helped oceans persist in a balanced state. Less friendly gases such as sulfur dioxide or methane, though causing storms and localized temperature shifts, contributed to critical chemical reactions for primordial organic compounds, the first building blocks of life. Volcanic activity at this time nearly covered the entire planet, not limited to fixed points as today, but spreading across the surface, linking land and sea. Lava flowed hundreds of kilometers, creating new plains and large basins where steam, minerals, and gases continuously interacted. Smoke, ash, and gases spread across the sky, dimming sunlight, reddening sunsets, temporarily cooling the surface, and regulating planetary temperature. In this state, Earth learned to balance itself through its own chaos. The islands gradually became more solid as basalt cooled, simultaneously expanded by successive eruptions. They formed outlines for the oceans, guided currents, and created primitive seas with continuously moving water. Sediments from islands fell to the seabed, rich in minerals and nutrients, enriching the marine environment and preparing the chemical foundation for early life. From space, the first Earth appeared both chaotic and orderly. Blue seas, undulating black basalt islands, dense clouds, and smoke columns rising from every direction. This was a planet learning to regulate itself. Fire, water, land, and air interacted continuously, creating a rhythm in which each smoke column or lava flow was a part. Everything expressed a living planet, exhaling from deep within, generating an atmosphere, filling oceans, forming land, and preparing for life. In the distant future, from small islands, vast plains and continents would emerge. But now we witness Earth's first efforts to create a stable surface, where water and fire no longer oppose but interact, where volcanic breath is both destructive and creative. It is within this chaos that life found its first opportunity. Every smoke column, lava flow, and grain of ash falling into the sea serves as a reminder that Earth is not merely an inanimate rock sphere, but a living entity, learning to breathe, learning to balance, and preparing for a more complex, greener, and potential-filled world. As the thick mist of early Earth began to lift, the oceans were no longer just murky, boiling puddles, but became vast laboratories where chemistry occurred continuously. Cooling lava flows, dissolved minerals, and volcanic gases created an energy-rich environment where simple molecules could collide, recombine, and develop into more complex structures. In the shallow regions along basaltic islands, the moderate temperatures of warm pools, heated by geothermal energy and enriched with minerals from lava, created natural reaction pockets. Here, carbon, hydrogen, nitrogen, and oxygen atoms began to combine, forming amino acids, nucleotides, and primitive organic compounds. These were the first building blocks, the letters of life's alphabet, slowly written through countless bubbling, colliding, and recombining reactions. Imagine this scene, the ocean foaming, each gas bubble from hot lava rising, mixing with water vapor, carbon dioxide, nitrogen, and sulfur. The young sunlight penetrated the thick cloud cover, ultraviolet radiation stimulating chemical reactions, while thunderstorms tore through the sky, providing electrical energy to split molecules. Each lightning strike was a test, creating opportunities for atoms to rearrange in new ways, forming compounds capable of long-term stability. Hydrothermal vents on the seafloor spewed superheated mineral and metal-rich water, creating crucial chemical gradients that drove increasingly complex reactions, from the combination of simple molecules to the emergence of longer chain structures. This was a delicate interplay of heat, pressure, minerals, and energy, all occurring simultaneously, millions of times across the primordial oceans. Volcanoes, often seen as destroyers, were in fact silent allies of life. Their fiery breath supplied carbon, nitrogen, sulfur, and trace metals, serving as raw materials for the primordial oceans to conduct complex experimental reactions. Each eruption carried lava, gas, and ash, not only creating new land, but also continuously providing energy and materials to coastal pools and hydrothermal vents. Within this chaos, an underlying order gradually emerged. More stable molecules accumulated, self-sustaining structures formed, and the foundations for life began to take shape. The famous Miller experiment was merely a simplified replica of what occurred billions of years earlier. When scientists generated methane, ammonia, hydrogen, and water and activated them with electric sparks, amino acids appeared naturally. On early Earth, this process occurred on a global scale, in diverse environments, from hot volcanic pools to hydrothermal vents on the ocean floor. Energy from lightning, ultraviolet light, and high temperatures produced countless reaction variants, while minerals and metals acted as catalysts. Each simple molecule was tested countless times, and some persisted long enough to accumulate, connect, and form longer, more complex chains. The primordial oceans were sites of simultaneous, continuous, and unceasing experimentation. Along volcanic island shores, dissolved minerals formed thin films where reactions occurred more readily, giving molecules opportunities to form more stable structures. Waves and currents created a natural mixing mechanism, ensuring molecules interacted, reacted, and underwent multiple cycles of testing. These environments were not random, but guided by favorable physical and chemical conditions, generating order from chaos. Here, chance encounters between molecules became patterns that directed later complexity. Over millions of years, long carbon chains, complex molecular rings, and nucleotides formed. The biological alphabet was gradually written, letter by letter, creating a primitive framework of genetic information. Gas bubbles from volcanoes provided carbon, nitrogen, and sulfur, while rain and tides supplied water, diluting and maintaining balance. Ultraviolet light and lightning provided energy, stimulating reactions, breaking weak bonds, and creating opportunities for stronger molecules to persist. It was a complex dance between chemistry and physics, between energy and raw materials, unfolding over millions of years across the planet. With each volcanic eruption, each rainstorm, each lightning strike into the sea, Earth both generated chemical mixtures and controlled the environment so that molecules capable of stability could persist and accumulate. Heat from lava, minerals from volcanic rock, energy from light and lightning, combined with water, all collaborated to create conditions suitable for the next leaps, from chemistry to biology. This was where the first living materials were cooked, preparing for the emergence of the first cell. Over time, volcanic eruptions became less frequent, the atmosphere began to stabilize, and the sky gradually cleared. Dust decreased, nitrogen became the dominant component, and reactive compounds gradually stabilized. The oceans retained minerals, dissolved gases, and heat, preparing the chemical foundation for life. Each foaming pool became a living laboratory where chemical reactions occurred continuously, creating the first opportunities for cells to appear. Looking back, the central role of volcanoes in this process cannot be overstated. They were simultaneously energy sources, material suppliers, surface shapers, and creators of ideal microenvironments for chemical reactions. Without them, Earth would have been mere lifeless water with no atmosphere, no minerals, and no chance for life to emerge. Thanks to fire, water, and energetic forces, the young planet began writing the first letters of the story of life, opening a new chapter in the history of the universe.